in this tutorial, I won't be going over a lot of different machine learning techniques that you can find in sklearn, for example. But instead, I'd like to lay out basically concepts that are common to a lot of machine learning techniques and that I think are a good foundation if machine learning is something you want to do. So I think these are the concepts that are a good foundation if you want to learn more about specific techniques later. And I should also say, next slide, there we go, that these slides are heavily based on these excerpts of these two textbooks. And I point them out because the PDFs for these textbooks are actually available online completely legally. So if you follow those links, the entire textbooks are available if this is something that you want to read more about. So to start off this intro, I thought I'd put up this kind of academic definition of machine learning. So, I feel like machine learning has kind of become this buzzword that gets thrown around. But what is machine learning actually? And here's one definition I've chosen that says, a computer program is said to learn if its performance at tasks as measured by some performance measure improves with experience. Okay, so this is a fine definition. This is the one that I follow. But what is this sentence really saying? Let's try to unpack it a bit. And to unpack it, I'll actually enlist the help of the University of Washington's animal mascot, Dubs, a Alaskan Malamute. So here's a recent tweet from one of the University of Washington accounts about Dubs. And let's say I'm interested in finding different tweets that contain the word or contain the string dog. And this is fairly easy to do, for example, in Python, if I've got a whole bunch of tweets ready and downloaded already to look at. And I can kind of summarize what I want to do with really one line in Python. I want to see whether the string dog is in each tweet I want to look at. And something very close to this line in Python is going to give me the answer that I want. And machine learning practitioners often call this sort of thing a rule-based system. And really, this is a lot of what we do in computer programming. We take some task that we want to do, and we break it down into small enough steps that a computer can understand so that then the computer can execute kind of this list of commands or this list of rules that we want and give us the answer. And so, this sort of programming is used everywhere. There's way too many applications to list. One example that's dear to my heart is PSF photometry, which you can summarize as kind of, first find a star, then, maximize the likelihood to find its position and brightness. And these are all things that I can write down as a list of commands for the computer to carry out. So I'm talking about rule-based systems here to kind of contrast them with what machine learning is all about. So finding the word dog in a bunch of text is pretty easy to do with a computer. Something that's much harder is, let's say I don't want tweets that have the word dog, but I want, pictures of dogs. So now I want to ask the question, does this image contain a dog? It contains Dubs. And, if you can see this picture as a person, this is pretty easy to do if you can see the picture and you know what a dog looks like. You kind of do it intuitively. But if you think about how to get a computer to do this, that's a bit trickier. you would love to be able to write this line in Python where there's some like dog object and you test whether or not it's in the image that you have, but I'm not aware of any programming language that allows you to do this. And the thing is, the image is fundamentally a bunch of pixels, and it's really hard to come up with a set of rules that reliably turns, a set of pixel values into whether or not there's a dog in this image. And so there's a lot of these kind of messier problems that we're interested in. One kind of astronomy example could be classifying images of different types of galaxies, like spirals or ellipticals. And Kyle tomorrow will actually be showing you an example of using neural networks to classify images of galaxies. So machine learning is all about, it's really an approach to deal with these kind of messier problems where it's not easy to write down a set of commands or a set of rules that gives us the answer that we want. Instead, kind of the fundamental approach in machine learning is that you collect a lot of data. So if we're interested in identifying dogs, it would be good to have a data set of a lot of dogs. So as one example, here's a Zoom call of a bunch of dog university mascots. And in this data set, we would also like to have things that are not dogs so that we can kind of teach the computer the difference between the two. So maybe we also throw in a data set of cats, or, it doesn't have to be other animals. We could throw in a data set with all sorts of random objects that are not dogs. And in machine learning, the approach is that you collect a data set that kind of addresses the task that you want to do, identifying dogs versus not dogs. And then you go through a procedure called training, and you construct a thing called a model. And you might remember that word from Josh's talk, and there's actually very good reasons why it's the same word. But in machine learning land, the idea is at the end, we want a model that's able to identify dogs. And the way that we get it is we collect a lot of data, and then we train this model, and eventually it'll be able to do the task that we set it. And so I'll get into more specifics on what this looks like. But I just wanted to say that this is kind of fundamentally what machine learning is all about, collecting a lot of data to train a model. And before I go on to the sorts of things that are possible with machine learning, I also wanted to pause for a second to talk about sort of the things that we should be cautious about whenever we use machine learning. And machine learning has gotten very popular lately, and it's used all over the place in our daily lives, especially online. And one really important thing to remember about machine learning models is that they're only as good as the data set that you trained them on. And one kind of amusing example is here's some examples of a model that's been trained to identify different breeds of dogs. But this model confuses Chihuahuas and blueberry muffins and Labradoodles and fried chicken. And you can kind of see why it does this. Like, sure, we can recognize the dogs in these images, but we can also see the similarities between Chihuahua eyes and blueberries, or Labradoodle fur and fried chicken.
That's hilarious. The Labradoodle in like the middle row, far left, actually looks like a piece of chicken.
Yeah. And so, that might even be confusing enough that a person looking at it might even get confused. And, the point I want to get across here is like machine learning does great things, but it's not magic. Like, it's based on kind of the limitations of your data set. And you can easily get kind of funny results like this. And kind of one thing I want to point out is, this example, I picked like a pretty fun example, right? Like fried chicken and labradoodles. But machine learning nowadays is often used with, data collected about people. And so this example is pretty funny, but you can imagine it's significantly, more consequential if instead of labradoodles and chihuahuas, we're talking about, people's credit reports or whether they get approved for different rentals. And so I just wanted to present the idea that, these sorts of weird quirks that machine learning models can have real world consequences, especially if you're handling people's data. In astronomy, generally, we're talking about data from stars or planets or whatever, so we might not have to worry about handling people's personal information. But I think that, anyone who uses these sort of tools is part of the societal conversation about machine learning. And so I think it's something that we should know about. And another thing that I'll point out on this slide is that machine learning models, don't exist in isolation. They can kind of interact with the sorts of things that are going on in society. And here I've linked to a paper that talks about predictive policing that tries to use data to decide, where to send more police patrols. And you can get into kind of these feedback loops where, let's say the data set you give it is biased in that there's more arrests in certain neighborhoods. Then your machine learning model might send more police patrols to those neighborhoods. And you'll get even more arrests in those neighborhoods, even if crime is happening elsewhere, just because that's where, you've used this model to send the police there. And you set up this loop where your model sees, oh, there's even more arrests there. I've got to send more people there. And really this model is kind of interacting. The way that we're using this model is having, kind of dangerous consequences. So this is a topic that I think deserves a lot of discussion. I've only got a short time here, but definitely feel free to, I'm happy to talk about this sort of stuff. So now that I've kind of maybe knocked machine learning down a peg, first I'll give a kind of brief overview on the sorts of broad categories that people put machine learning applications in. So you'll often hear the term supervised learning. And here I'll introduce kind of the standard vocabulary that people use. So in supervised learning, you have a data set that has kind of two categories of things. It has features and it has labels, or sometimes the labels are called targets. So this dog problem I've been talking about is an example of supervised learning. The features in my case are the values of each pixel in each image. I can think of those, I've got a set of numbers that correspond to each pixel, and that's kind of my set of features. But a feature can be sort of anything. It can be any sort of number. And there are other applications where features might actually be words if you're doing like natural language processing. So in supervised learning, the idea is you have a bunch of features that you want to use to try to predict a target. So in my dog case, I'm using the pixel values in each image to predict whether or not that image has a dog. So dog or no dog is my label or my target. And supervised learning is often broken down into two categories. One being classification, where your target value is a category or something discrete, like dog versus no dog, or you can imagine something that's like dog, cat, or other. And people often talk about regression, where your target is not a category, but instead a number. And so one example of regression is the sort of models that are behind the scenes of the Zillow Zestimate, where the features are things like how many bedrooms does a place have, how many bathrooms, what's the square footage. And recent models even include like the text describing the house and even the pictures. And their target is, what is the sale price of this house? And that's kind of the thing that they're trying to predict using all of the features that they've collected. So supervised learning is often kind of placed in contrast with unsupervised learning. And at least I feel like I don't have a good definition of unsupervised learning. There might be a better one out there. But I think of unsupervised learning as saying the data set only has features. There's not a target that we're necessarily wanting to hit. But we just have a data set and we want to learn something useful about kind of the structure of the data set, like what's going on in this data. And one kind of cool recent example of unsupervised learning, if you follow this field, you may have heard of generative adversarial networks, or GANs. And these are pretty interesting because you can give them a data set of human faces, for example, real images of people. And using unsupervised learning, this GAN kind of learns what human faces look like, and it can generate new pictures of new faces that weren't in its data set. And so, there's this website called thispersondoesnotexist.com that shows you, faces that this GAN has made up that don't correspond to any of the images that's been given. And so, it's learning something about like what patterns of pixels correspond to human faces. And it seems to do a pretty good job. But I think...
Yeah, that's crazy. It's like it gets the structure as well as the colors so well.
And I should also, there's always an asterisk for, all of these things. So you can also worry about the representativeness of the data set it's been given. But it's still impressive, like how much detail this GAN is able to make. People often talk about this dichotomy of supervised and unsupervised, but I really think it's kind of a spectrum. As an example of something that's in between, in the natural language world, there's this model called GPT-2. And it's sort of supervised because what it's trained to do is if you give it a bunch of writing, its target is to predict the next word that comes in the sentence. So it's kind of supervised because the features are the previous words. The target is the next word. But I would argue it's also sort of unsupervised because you can kind of let it loose and give it, the sentence that sounds like it's out of Lord of the Rings fan fiction and just have it keep predicting the next word. And it ends up writing Lord of the Rings fan fiction with Elrond and Gimli hanging out. So it seems to be learning something about the structure of English, at least. And also it's learned that if Legolas and Gimli are hanging out, Aragorn's not far behind. So this really seems like it's learning something about, what people write about, which is pretty cool. The kind of third category that people talk about is reinforcement learning. And in reinforcement learning, there's not a fixed data set, but instead there's the model kind of lives in a virtual environment and kind of collects data by acting on this environment. And kind of one application that's gotten a lot of attention lately is using reinforcement learning to teach computers to play games. One example that I particularly like is the model Alpha Star, which actually plays StarCraft 2. And kind of with similar limitations that a human would have playing the game, it has to move the mouse around and stuff like that. This model was actually able to achieve Grandmaster level performance on the European server in StarCraft 2. And it did this by the data set that it had included games that human experts played against each other, but it also, AlphaStar also played StarCraft games against itself to kind of generate data that it could learn from. And so I think this is kind of a very different way that machine learning can work, and I thought I'd point it out as one of the categories. So now that I've talked a bit about, what sort of things you can do with machine learning, what does it actually look like to build a machine learning model or to train a machine learning model? I think there's kind of 4 big pieces that you need. You need a data set. That's the whole deal with machine learning. You need a lot of data to train on. You also need to define a loss function. And this is, connecting to Josh's talk. Like, he talked about a loss function or an objective function, and he also talked about different choices you can make there. You do the same thing in machine learning. In machine learning, you also choose a model, and sometimes people will call this the architecture, but you have to pick a class of thing you want to use, and I'll give you a couple of examples later on in this talk. But you have to have something that is trainable. And then finally, you need a way to train it or a way to optimize it. You need an optimization procedure. Now, this might seem a bit abstract right now, but Josh actually perfectly gave an example of machine learning. Like he said, linear regression. So let's say I had this table of the redshifts and distance moduli of type 1a supernovae, and I wanted to learn more about how redshift and distance modulus relate to each other. And I think Dustin will actually be talking about this problem in more detail tomorrow. So if I wanted to do linear regression or machine learning on this problem, I should define a loss function of some sort. And this loss function should, let's say I want to predict distance modulus given redshift. So I want a loss function that compares my prediction that I've called mu hat here with the value that's in the data set, which is just a mu. And the default is the L2 norm, or p equals 2. So here's, chi-squared. And I'm just going to say, okay, this is just the loss function. And the kind of simplest model that we can fit is mx plus b, or I've decided to use the notation a plus b times z. And so in this model, I have 2 parameters that I need to learn, a and b. And so I also need an optimization procedure to find kind of the best values of these 2 parameters, a and b. And Josh showed us the minimize function. And essentially what that function is trying to do is it's trying to solve this system of equations where the derivative of the loss function is 0 for both parameters. And that tells us we've got a minimum of the loss function. And so, in a lot of detail, Josh showed us that this is one of the, this is his maximum likelihood estimation of a straight line, ignoring the errors. And for this data set, like, the line sort of fits, but it also looks like there might be some curvature here that I might care about. So in machine learning, people often talk about the capacity of their model. And this corresponds to making your model more flexible. So one way that I can increase the capacity of my model is to make it a bit more complicated. So instead of fitting a straight line, I can add a quadratic term. And this actually looks like a slightly better fit to the data. Again, I'm doing chi by I, as Josh called it. But this looks like a pretty cool fit. So why don't I go even further and add on, even more terms like a cubic or a quartic term? If I go all the way up to order 5, I can actually make my model predict all of the data points exactly and make my loss function exactly 0. And so why isn't this the best thing to do? So yes, my loss function is 0, but I get this kind of funny quintic shape. And maybe I know enough about the physics of redshift and distance modulus to say, I don't think the real relationship has this kind of funny shape. I think it's, smoother than this. And one way we can think about, this kind of unease that we have with this quintic model is to talk about generalization error. And this is just codifying the fact that we want our model to do well on data that it was not trained on data that it hasn't seen before. So if we imagine measuring a bunch more supernovae and putting them on this plot, let's say we had another set of supernova that we did not use to train our model, and let's call it a validation set, and let's color it in orange. So what we can see here is that our quintic model, our high capacity model on the right here, it perfectly explains the blue points that it was trained on. But for example, these 2 orange points on the right, it's way off. Like the data is down here while the quintic is, shooting up into space up here. And so this seems like a very bad thing that we don't want to happen. And we call this overfitting because it's kind of taking the training data too literally, it's fitting it perfectly, but it's not going to do well on new data on the validation set. By contrast, a model that has low capacity, like the linear model on the left here, doesn't do well on the training data or the validation data. It's kind of doing poorly on both. And that's because this model isn't flexible enough. We can only fit straight lines with it, whereas, something with some curvature seems to actually be happening here. And in the machine learning vocabulary, these choices that we have, like how big of a polynomial to use, are often called hyperparameters. And they're called that because the coefficients like A and B are kind of your normal parameters, and these are kind of a level above them. These are the hyperparameters. And the idea is with a validation set, we can choose the hyperparameters that do the best on the validation data instead of the training data. And what this graph on the right kind of represents is in green, you've got the loss function on the training data as a function of capacity. So you can think of like our straight line is on the left-hand side and our big polynomials on the right-hand side. So if you make a model more flexible, you give it more capacity, it'll always do better on the training set. But if you look at the validation set, there's kind of a point in the middle that's close to optimal, where the model is flexible enough that it can explain the data, but it's not so flexible that it's perfectly fitting the training data kind of at the expense of everything else. Another thing I'll mention on this slide is that if you're comparing to a model that somebody else has made, it's also good to have an even more separate test set because just like the training data was used to find the best parameters for the model, the validation set we're kind of using to find the best hyperparameters to choose, where in the middle we should be. And so to do a really fair comparison to something that someone else has made, we should compare on a different set called a test set. So now that I've talked a bit about this linear regression example, you might be wondering, like, okay, what's the difference between what I've said and what Josh was saying? Like, isn't machine learning just a different way to look at statistics? And this is an easy way to start arguments between people. So I'll just cite two opinions. One, this blog post by Larry Wasserman that kind of says, they're both getting at the same question. How do we learn from data? We have a bunch of data. How do we learn stuff from it? And that they're just kind of two different approaches. My take is that it's hard to draw a hard boundary between statistics and machine learning, but I think something is more like statistics if you have a model that you might actually believe. So in my supernova example, I have no business fitting random polynomials to the data if I have a model of cosmology that I actually believe. So what I should actually be doing is, like Josh said, thinking about the generative model. I should be thinking like, all right, the two numbers I need to know are the Hubble constant and how much matter and dark energy there is in the universe. And from that, I can calculate the expansion history. And then from that, I can calculate the redshift and distances of all these supernovae. And so maybe I should actually be fitting for these kind of cosmological parameters that actually correspond to physics. Whereas I think by contrast, the idea in machine learning is that you don't believe the parameters in your model actually have anything to do with physics, but instead you're trying to use a really flexible model and you're going to throw a lot of data at it and just kind of see what happens. And I think, this is a useful starting point, especially if you're not sure what the right model is. So my last slide for this section is just this kind of zoo of the different machine learning models that are in the Python library scikit-learn that we're going to use in the notebook. And all of these models are called classic machine learning. And I think that's just to contrast them with neural networks that Kyle will talk about tomorrow. So before I go on to that notebook, I wanted to pause here and see if there were any questions about the material so far.
You may have said this, but which of those algorithms were supervised versus unsupervised, or did any of them kind of lie in that valley between that you were talking about?
So that's a good question. And is my slide still up?
Yeah, it's back.
Okay. Yeah, so there's kind of these four bubbles here. And roughly speaking, there's the classification and regression bubble, which are the supervised algorithms. And then down here, you've got clustering and dimensionality reduction, which are unsupervised. And I think to get something in between, you can kind of sort of combine, if you come up with a procedure that kind of combines two of these across the category, that's kind of how you can get something in between.
Cool, thank you.
Any other questions? All right, if not, I will pull up the example notebook I've made. Did Zoom switch to the notebook or is it still on the PowerPoint?
We can see the notebook.
Okay, great. So if you want to follow along, this is in your home directory. There should be Astro Hack Week 2020, and this is in the Machine Learning 1 folder, and it's the decision trees IPython notebook. So like I said, there's tons of different algorithms in scikit-learn. I decided to only focus on one and kind of show you how to use one of these algorithms in detail. And oh, I think I see chat. An example of reinforcement learning in astronomy. I've heard about people thinking about using reinforcement learning to do telescope scheduling. Like, you can kind of phrase it like a game, like, here are all of the things that I would like to observe tonight. What's the best kind of path for the telescope to slew between all of these objects, kind of getting the best observations and like kind of wasting the minimum amount of telescope time. I'm sure there's other examples that I'm less aware of. All right, so here, let's make sure this runs. Just have some input cells to import everything that we'd like. So in this notebook, and let me make it bigger too. There we go, bigger text. In this notebook, we'll be training a type of model called a decision tree. And as an example of a decision tree, here's an example that I made up for classifying different types of astronomical objects. And in a decision tree, it's made of nodes, and there's a root node that you start at. And the root node is a binary question about whatever you want to classify. So maybe I can ask, okay, do I have a compact object? If yes, I go right. If no, I go left. All right, let's say I have a compact object. Answering that question brings me to another node, which can be yet another question, like the game 20 questions. So if my object has an event horizon, I go right. Okay, great, it's a black hole. Like, I've come to the end of a path in the tree. I've come to a leaf in the tree. And this structure is called a tree because if you flip it kind of upside down, it vaguely looks like a tree. So you kind of navigate these nodes, which either have binary questions or they'll bring you to a leaf, which kind of tells you the final classification that you want. And so this, this is sort of a conceptual decision tree. But in practice, these binary questions are going to be questions about the features in your data set. And the questions will only involve one feature at a time. And we'll see an example of this. So we have, the model that we want to train. Another thing that we need is a loss function. And for now, I'm just going to use kind of the default scikit-learn loss function, which is called the Gini impurity. And if you look at the Gini impurity, the idea is, let's say you've got two classes of objects that I'm going to call minus and plus. The idea is you run all of these objects through your decision tree, and they'll land in different leaves of the tree. Ideally, we want each leaf of the tree to have either all positive examples or all negative examples. But in practice, we're probably going to get leaves that contain a bit of both. So let's say we have a leaf that has n minus negative examples and n plus positive examples. You'll notice that this loss function is 0 if either n minus is 0 or n plus is 0. So this loss function is minimized when our classification is perfect. We have examples of only one class in that leaf. And then the loss function increases if we're in between, and I think it's maximized for if you have half and a half, which is kind of just the same as flipping a coin. So we have a loss function. It may or may not correspond to a model that we actually believe. For now, we're just going to run with it as a loss function. We also need a way to train our model, to optimize the parameters of our model. And so just, again, to remind ourselves of what the parameters are. The parameters are actually going to be, what are the questions we are going to ask and what order should we ask those questions in. And the way that scikit-learn makes decision trees is it does it iteratively. You start out with just a root node, just a single question, and you choose the single question that minimizes this loss function averaged over the 2 leaves that you get by answering just that single question. Then you build on it iteratively where now you've got 2 branches, and now you find the second question that minimizes the loss function of the kind of 2 new leaves that you get. And you keep on doing this, like adding questions until you decide to stop. And so a tree, so just like in our previous example, if you have a polynomial with more and more terms, that's more flexible, it has more capacity. A decision tree becomes more flexible the deeper you allow the tree to be, the more questions you allow it to ask. So the deeper a tree is, the greater its capacity will be. In this example, we'll be using the Astro ML library, and it actually gives us easy access to a cool data set that has a bunch of RR Lyrae stars. And if you execute the cell for the first time, it might sit there for a minute as it downloads the data set. And in this data set, we're going to be doing a classification problem. We have 93,000 stars, and we have 4 features for each of them. We have these 4 colors, U minus G, G minus R minus I, and I minus Z. And we also have 2 possible labels that each star could have. And in this problem, a star is either non-variable or it's an RR Lyrae. And so using the features, using the colors, we want to try to predict the labels. Is this star an RR Lyrae or not? And one thing that's often important in machine learning, in classic machine learning at least, is feature engineering. And here, one example of feature engineering is that you can see that in this data set, we've decided to use the colors instead of just the raw magnitudes. And one reason we can use to kind of justify this is if we had 2 identical stars, but they're just at different distances from Earth, they would have the same color, the same colors, but different magnitudes. But they're really the same, they have the same intrinsic properties, so we should treat them the same. And so this is a choice that we've made about, what features to use and kind of how to combine them. Another thing that I think is good practice whenever you do machine learning is to do some exploratory data visualization that Fernando and Peter talked all about on Monday. Here, I've got kind of a simple data set that has only 4 features. So I can actually do a simple visualization called a corner plot. And don't worry too much about this code. This code is here in case you don't have the Seaborn package, which does this automatically. And I'll zoom in for this, zoom out for this plot. So here I've basically made scatter plots of all of the different pairs of colors that you could have. And the RR Lyrae I've highlighted in yellow, and the non-variable stars I've highlighted in purple. And kind of the first thing we want to see is, do we think we can use colors to actually tell the difference between RR Lyrae and not? And it seems like, okay, the RR Lyrae kind of live in this blob that's different than the blob of non-variable stars. So it seems like there could be, it seems like we have a chance here. Like this seems like a reasonable thing to do. Things we might be concerned about is, do we understand these hard cutoffs in color space? And it turns out we do. This is just how the data was selected, how we went to the database of stars. And we just basically drew a box around where we think the RR Lyrae are. So that seems okay. One thing we should be aware of is our model is only as good as our data set. And our data set has RR Lyrae and standard stars, like non-variable stars, meaning stars that we think are completely constant. There are stars that are variable, but not RR Lyrae. And those are not included in our data set. So if our model is going to be applied to some other sort of variable star, we probably shouldn't immediately trust the results that we get because it hasn't been trained on other types of variable stars. It's only been trained on RR Lyrae and stars that are not variable at all. And in practice, there's all sorts of different visualizations you could try to make to understand your data. So zooming back in, scikit-learn has this function that allows us to split our data set into a training set and a validation set. And to illustrate why the validation set is so important, I have this example here where we're going to use scikit-learn to train a decision tree. And scikit-learn is great because it makes the code for this pretty simple. What you do is you kind of create your model. So you say, I want to make a decision tree. This random state, make sure that, as an example, we're all going to get the same decision tree out at the end if we put in the same random state. And one of the hyperparameters that we have to set is how deep we want the tree to go. So this comment is actually wrong. This tree has a depth of 20. Then we train the decision tree using this fit function, and we give it the features and the target. And I've put this timing command up here so we can see how long it takes. And even though we've got 100,000 stars, this is pretty fast. It only took 150 milliseconds. That's pretty great. So we've trained a decision tree in 2 lines, which is awesome. And if we want to look at how this decision tree is doing, we could look at the loss function, which is the Gini impurity, but we actually don't, it's hard to interpret what that really means. We might be more interested in what I'll call precision and recall, or in the astronomy literature, you might be more familiar with completeness and contamination. So the idea behind recall is in our data set, there's a bunch of RR Lyrae that are there. Our decision tree is going to find some of them, maybe all of them. So recall answers the question, what fraction of the RR Lyrae does our decision tree actually find and identify correctly? Precision is a slightly different question that asks, if we use our decision tree to predict whether a star is an RR Lyrae or not, it'll identify some candidate RR Lyrae. Precision asks the question, what fraction of those are truly RR Lyrae? When our decision tree says that something is an RR Lyrae, what fraction of the time is it right? And if we evaluate the recall and precision of our decision tree, and again, scikit-learn gives us all these functions to make it easy. To calculate the recall, we give it, we say that we want to compare the targets in the training data, Y-train, with the predictions that our decision tree makes. So what happens if we feed in the features into our trained decision tree? And notice here that we're using the function predict. So this is no longer training the decision tree. Instead, we're just using it in its current state. And here we can see that evaluated on the training set, the recall and precision are perfect. They're both 1, they're 100%. Okay, great. We've solved our lie rate classification. Except not so fast. If we instead feed in the validation data set and calculate the recall and precision, we can see that our recall and precision are actually much worse than the training set would suggest. In fact, both of these numbers are around 50%, which is kind of what you'd expect if we were just kind of guessing by flipping a coin. So this is really showing us that a decision tree with 20, with a depth of 20 is actually overfitting. It's perfectly predicting our training data, but it's not doing so hot on the validation data. And so this is why it's important to have a validation set, because otherwise you might trick yourself into thinking that you've got a really good model when you actually don't. So I'm just going to pause here.
So Stephen, going back to that.
Sure.
I'm sorry, going back to that plot you had where you showed the loss as a function of complexity. Sorry, it's not here. I think it was in your talk. But so you're just saying we've kind of gone way past that minimum.
Exactly. And does the slide show up now?
Yes.
Okay, yes, exactly. So yeah, it seems that a tree with a depth of 20 has a very high capacity. And in fact, it's such a high capacity, we're somewhere on the right-hand side of the plot where we're doing really well on the training set. We're at 100% on both metrics, or like 0 loss function, but we're doing much worse on the validation set. So we've kind of overshot how much capacity to use. So, all right, let's dial it back a little bit. And again, this is a hyperparameter that we're choosing. Let's dial it all the way to the other direction. Let's dial it back to 4. And we'll actually pause to take a look at this smaller decision tree that we've trained. So, same sort of procedure, except I just replaced the maximum depth with the number 4. And scikit-learn actually gives you a function that plots the tree. Unfortunately, at least with my matplotlib skills, the tree shows up with really tiny text, even if you make the font size really large. So at least the best way I've found to explore this tree is to actually zoom in on it. But I thought it was worth pausing here to check out what one of these trees actually looks like. And you can see that the first question it asks is the G minus R color less than 0.2? And it doesn't label it here, but it turns out if the answer is no, you go left. If the answer is yes, you go right. And so you can actually see that these questions are questions about individual colors and whether they're equal to or below some threshold. And one thing we should also notice in this tree is that the non-variable stars outnumber the RR Lyrae a lot. And so if we look at our leaves, kind of the end of the tree, there's only one box that predicts that anything that lands in this box is an RR Lyrae. And so, we probably don't expect this tree to be doing that well. And given that it's 40 past already, I'll skip this next plot, although definitely feel free to ask me about it at coffee. Let me look at the chat here quickly. Yeah, so decision trees, I think if your features are like real numbers, the decision tree is always just picking a threshold and asking whether you're above or below that number. Yeah. If you have discrete features, like maybe you have a feature in your data set that says, does this star have an event horizon? And maybe that's just yes or no. Your decision tree might instead have kind of an if statement there. So I think the last thing I want to show here is to dive into this idea of hyperparameter tuning. So I've shown you a tree with a depth of 20 and a tree with a depth of 4. But really, we'd want to go kind of in between and see like what the best hyperparameter is. And so here, what this code does is it tries out all of the depths between 4 and 11, and it'll calculate the precision and recall of all of these different trees. So if you run this, this is kind of analogous to the plot that I showed in my slide where, you know, we've got the loss function. I should have labeled my y-axis. Loss function on the y-axis and capacity on the x-axis. Here we've got tree depth on the x-axis and precision and recall on the y-axis. So I zoom out a bit here. If we look at recall, on the left, we've got a decision tree with the depth of 4, and it really seems to not be doing well at all. It's underfitting. Its recall is less than 10%, both on the training set and the validation set. So that doesn't seem great. If we dial up the depth of the tree, the recall goes up. So our tree is doing better and better. And if we get up to a depth of 10, our recall is above 80%, which maybe we would say is good enough. You know, maybe this is a good enough model to use. But we should be looking at how the model does on the validation data. And you can see that a tree of depth 10 actually does much worse on the validation data than the training data. And so by depth of 10, it really seems like we're overfitting. One way we can choose what tree to use is we can say, what model does the best on the validation data? And in this case, we would choose this model here, a tree of a depth of 5. And that gives us the best recall on the validation set. One kind of subtlety is that the best model depends on what our goals are. So if our goal is to find all of the RR Lyrae, and we don't mind getting a few false alarms, like we don't really care if we identify some candidates that turn out not to be RR Lyrae. We just want to find all the RR Lyrae we can. 5 is the best depth. But if our goals are different, if we want the best precision, so if we want to be as sure as possible that when our tree says something is an RR Lyrae, that it actually is, because maybe we're going to follow it up with a really big telescope that's hard to get time on, we might want the best precision. And we should look at you know, which model gives us the best precision on the validation set. And that would actually tell us to use a tree depth of 7. And depending on what your goals are, you might actually want to optimize for some sort of compromise between precision and recall. So maybe 6 is a reasonable depth to use. And I think this is part of like the art of using these models. Like the best model depends on what your goals are. And it's good to have some sort of metric that you think captures what your goals for the model are.